This is Zhonghan Wang from Institute of Software Chinese Academy of Sciences, and I'd like to introduce a new local search framework for nonlinear real arithmetic for SMT problems. The first section is about syntax of SMT NRA and the traditional fragment of local search. As an arithmetic problem, SMT consists of the basic structure of set problem, and it consists of basic is the formula structure. F can be an item and the negation or some logical combinations of the items. And in arithmetic expressions, we define the item to be a Boolean variable or a polynomial, and we detect the sign of it. You mean we can define the polynomial with positive or negative ones. And as we say, nonlinear arithmetic, the polynomial can be times itself or other polynomials to become a great one. The satisfiable problem is to determine whether the formula is satisfied by some assignment, and in this case, the local search focuses on finding some assignment that can satisfy all the formulas. Or we can say that we can prove unset for this instance. And here is an example. And you can replace all the variables with the assignment below, and you can find that the formula is satisfied. This frame introduces the framework of local search, and if you are familiar with the local search algorithm, you can find that it begins with the initialize of the assignment. In this step, we initialize the arithmetic variable to 0 if the lower bound and upper bound contains the 0, and otherwise we choose some random values, and actually it's some integers, and we don't use some irrational values for them. In a while loop, and we do critical move procedure to try to decrease the number of unset clauses, and sometimes the number of unset clauses maintains still. The while loop terminates in two cases. The first case is that the problem is done and all clauses are satisfied, and we really found the assignment. The second case is that you give a time, and the time consumed has enlarged, and it's over the step limit. This algorithm is about critical move procedure. Critical move actually introduces the concept of flips in set solving. According to the make-break score, we define the variable and the new value and the score to move in the next step, and if we actually get a positive score, we move that word to the new value. It's called the greedy part. Otherwise, we say that we cannot find a variable and a new value combination to decrease the number of unsatisfied clauses, and in this case, we update the clause weight according to some schemes. And actually, after the clause is waiting and the structure of the whole problem has changed, and the score computation is different from the previous one, and in this case, we can do critical move making the clause that has changed to make it satisfied. We try this step for 3 times, and if we still cannot find some improved steps, we return this step, and we go to the next iteration. Here is a table for difference between set and SMT solving. In set solving, operation usually means flip. It means we change some true values to false values and false values to true values. However, in SMT, we all know that arithmetic values don't have true or false values, and we can only move them to some critical values to make the literal or obviously the polynomials to change their signs. The score definition is the same for all set and SMT local search fragment. It is summed by weighted unset clauses. And the third one is a new skill, is a new innovation that we introduced for SMT solving. If you are familiar with local search in set solving, you can know that set solving, the score of flipping a Boolean variable is cached before the step is moved. When we flip a Boolean score, the score of that of the whole Boolean variables are computed, and in SMT this cannot be done because we don't know which value should we move the variable to. And this introduces scoring boundaries. Okay, here's some basic definition. If it's in the invisible set of a clause C with respect to an assignment is that what in the set of values that the variables in the clause can take under the assignment, such that the clause is unsatisfied. And we know that the set may be empty and may be a full set. Here's an example. Assume that x takes the value of 1 and the two clauses of that contains x can all get some invisible set. The first one that x can only be some value that if x takes 0, the clause is satisfied. Otherwise, it is always unsatisfied. The second part that we introduced the make-break intervals. The make-break intervals is a combination of invisible or visible intervals of arithmetic variable to all clauses. The difference of make-break interval and the invisible set is that when we see an invisible set, it is to a specific clause C. But make-break interval, it's usually to an arithmetic variable, not to a specific clause. Actually, it's a combination of all invisible intervals. So in the previous example, let me see that if x takes the value lower than -1, the score is 0, and otherwise it gets a different score. In this section, we introduce the traditional computation for the best critical move score. Actually, as we see previously, the critical move score is computed after the step procedure. For each unset clause C with variable v, we compute the interval score info of v in C. And actually, you can see that the complexity is v times C. Then we combine the interval score information and update the best variable value move. Then we return the best critical move. But here's some repeated computation. The first one is a variable invisible set. Actually, two steps that is adjacent in the local search. They share most of the variables invisible set in most clauses. And the second one is a clause set status, because in most local search iterations, many clauses stay their set or unset status. We define the definition of boundary. A boundary is a first tuple where the value is a real number. The real number defines the value that the arithmetic variable returns to, and is open that whether the value is active or not. That at that point, it also means make or break. It means that we increase or decrease that score. Also means that we increase or decrease the number of unset clauses. The last one is CID, and it is a causing clause, and in which clause that causes the interval that the variable assigns. Finally, we sort the boundaries to the leftmost to the rightmost, ordered by the value. And if the value are the same, we order by the is open Boolean variable. Okay, here's a previous example, and you can see that the boundary set of all clauses are computed according to their invisible set, And in the first example, it's a special one that because y assigns to 1, that x can only assign to 0 to make the clause to be satisfied. In this case, that 0 has a different different score with all other values in the real space. So we introduce 2 boundaries for this clause, and other clause only have 1 boundary set. The sorted boundary set have 4 elements, and it looks like that. Next is that how we compute the score using the boundary. The starting score means that the score when x moves to negative infinity, and it is computed by the starting score 0 plus 1 minus 1. It is still 0. Some other scores on the real space is computed by the increasing or decreasing the score on the boundary set, and actually we can get the score boundaries on the whole real space. The second problem is that how do we maintain or change the boundary set? We only maintain the boundary info unless the neighbor does a critical move. Actually, if we does a critical move, and all these neighbors have to change the boundary set. Here's an example. Assume that variable v is modified, and we output the score for all variables. Note that v does not appear in all clauses, and in some clauses, some variables in feasible set does not change. We loop all the clauses that contains v, and we loop all the variables appearing in the clause, and we record all the variables to the set of S, and we compute the starting score and the boundary with respect to the clause. Finally, we recompute all the best critical move and score in terms of boundary information. This algorithm is done after the critical move procedure, not before the critical move procedure, so it is computed after the step, and after one step, and we know the second step, what is your critical move if it usually selects the best critical move. The second section is about the temporary relaxation of equalities. Here the equality doesn't know the strict equality, and it means non-strict inequalities. Previous work and introduced some definition of value complexity. Usually, irrational numbers is more complex than rational numbers, and if 2 values are all rational numbers, we compare with their denominator. Our solution is introducing relaxation to enlarge the point irrational interval. Here's an example. And in all of these clauses, z can only to be an irrational number. It's not an interval. It's not a point interval. And we do relaxation to the equalities. If the constraint is from p strict to 0, we split the form to p minus or p positive than epsilon p. And also, if the form is positive or negative, we enlarge it by a very small value. The select var that we record for each select clause is the var that is being assigned. We usually do relaxations when it's a lazy procedure. Usually, when we have to force a variable to an irrational number, we do relaxations, not by pre-processing. The next algorithm is about restore. Restore means that how can we get the accurate value to some variables to get the final correct answer. If we have some clauses select, and we should output whether all these clauses should succeed or not. We loop all the selected clause, and we record the selected variables in clause, and we try to move that variable to the accurate value. Also, if you move the variable to the accurate value, its value changes, and it may change some clauses set out or unset some status, and the whole score of the unset clauses may change, and it may not be succeed. Finally, if we use incremental computation of boundary set, we recompute the best critical move and score in terms of boundary information. Whether succeed or not, we see that the number of unset clauses is equal to 0. Here is the whole algorithm with relaxations and its main part is a traditional while loop, and here is the example. Here is the difference that if all clauses satisfied, we do not return succeed after that, because some clauses may be slacked, and we try to restore the relaxed constraints to original form. If we find that the exact solution by the local search is still succeed, then we return the succeed with the assignment. Also, the restore procedure also can bring some difference to the score and cause some satisfied clause to be unset. This flip results in the failed in the local search algorithm, and we still to return the local search algorithm to maintain and decrease the unset clause numbers. Here's the implementation detail. The first one is pro-processing. And in SMT lab, many polynomials have the form of both negative or equal and positive or equal, and we should combine them to the equality. The second one is that we eliminate the variable in an equation of the linear form. In local search, we use the restart mechanism, and both in minor and major restart. Minor restart usually means that we randomly change one of the variables in the unset clauses, and in major restart, we reset all the variables values. Maybe we are stuck by some same cells in the search space of the SMT NRA, and we want the major stack to jump that cell and to a totally different cell, and so we reset the value of all variables. The last one is about overall result, and here is ours. We beat all some traditional solvers in the set instances. All these instances are satisfiable, and we erase the unset instances detected by other traditional solvers. Unique are the instances that can only be solved by ours. The first category, that MBO, it only consists of polynomial of very high order, and it detects a polynomial sign. So some traditional Z3 or CVC5, it uses MCSAT to split the search space, and they stuck in this category. Here's a scatter plot, and we record the time consumed to solve an instance. Ours is in the horizontal line, and other traditional solutions in the vertical lines. The final one is a comparison of temporary relaxations of constraints. This usually is very helpful for the instances that has equalities and non-strict inequalities. And it brings us some 80 more instances solved than some other algorithms. Okay, here's some conclusion that we bring a new scoring method for SMT NRA, and we catching the clause information for arithmetic variable and only change them after the critical move. The second one is about a new method to handle the inequalities, and we enlarge the irrational interval temporarily and speed up the whole solving. Here are some future work. The first one is about catching about cylindrical cells by CD. In current existing local search in nonlinear real arithmetic usually operates move on variables, not on cells. and usually we enter the same cell multiple times, and how can we find the same cell repeatedly? The second one is that we should incorporate with other algorithms like MCSAT or some other complete algorithms. And final one that we plan to introduce this algorithm for nonlinear optimization. Okay, thank you.
Questions? Oh. Thank you very much for a nice talk. And so you, am I right that you are focusing on satisfiable problems? So can this algorithm in principle be expanded to generate also proofs of unsatisfiability, like the NLSAT?
Basically, local search can only solve satisfied instances because it initializes assignment of variable and it changes to try to make the unset clauses to 0. And in this case, it can't help to prove unset for a problem. But some existing work that if you don't use the poor local search algorithm, it can usually help you to find unset proofs. For example, at some existing work like they use local search to boost CDCL, for set solving, and because local search always they help you to prune the search space.
Right. So generated if you incorporated this into an algorithm.
Yeah, if you incorporate it, it can help you to generate proofs.
Okay, thank you. Any other question? So I do have a question. Okay. In order to better understand your algorithm, for instance, what would happen if you would to run your algorithm on the conjunction of linear equalities? Would it degrade to behaving like a variant of simplex, or would it do something else?
Actually, this work, this work is about nonlinear instances, but it also works on some linear instances, and maybe there are some local search works that combine with simplex method on linear ones, because linear ones usually have some simpler algorithms than nonlinear ones.
But what I was wondering is, if you were running your method on a conjunction of linear inequalities, would it behave in essence, would it mimic what simplex would be doing, or would it do something different?
Maybe different.
Okay. Another question? It's time to speak. Oh, okay. Could you just clarify the representation that you use for satisfying assignments? Are they floating points, or are they exact arithmetic, or do you kind of multiply everything away? You were mentioning integers, but I didn't understand that part. Well, so do you use floating point numbers in your implementation?
Floating numbers always say rational numbers and irrational numbers. Floating numbers consist of rational number and irrational number. When we say irrational number, like the square root of 2, the square root of 2 in Z3 is not defined by a simple floating number. It is defined by a polynomial square root.
Okay, and so the main consequence is that you said you move away from them, right? Then you end up considering some other rational approximation of them, right? Yeah. My question was just, if you implement this, you could use exact arithmetic, or you could use something like double?
In the local search fragment, you can use double or float, or anything that can represent rational values.
And you happen to use doubles?
No. In our code, it's written in CPP, and in our code we use types from Z3. these three MCSAT algorithm, and it uses rational. It's different from floating value. But if you insist on floating values, it works again.
Okay, thank you. Next time, the speaker again.